This is a video in which we're going to discuss one-way analysis of variance, or Anova, and we'll primarily focus on what are called multiple comparisons, a companion testing method that is used with Anova. You recall in two-sample t-testing, we look for a difference, a mean difference between two populations. Well, it turns out this test naturally generalizes to what is called one-way ANOVA, or analysis of variance. And in one-way ANOVA, the basic difference is there are more than two populations or groups that which we wish to compare to see if there might be differences between them. And I'll assume you have read through the notes on one-way ANOVA, which should help you understand the method. And our goal here is to primarily just show how it's done in JUMP, give an interpretation, and then show what we call multiple comparisons. So I'm going to illustrate ANOVA, but as I said, my focus will be on something called multiple comparisons. And I've decided to use a different data set than in the notes. And this is data from the anodized parts case study, chapter 6 of the Visual Six Sigma book that we have been discussing and you've been reading about. And what we have is some observational data that's been taken on 240 parts that have been anodized. That is, they've had a corrosion protection applied to an aluminum surface, and then they have been dyed black, and the specification requires a blemish-free, rich, dark color. And after the parts have been anodized and dyed, they're then inspected and they're broken out into three categories. Smutty black, this is a highly blemished surface. Normal black, this is acceptable. This is what the customer wants. And purple black, which is also unacceptable. This is a surface which, instead of black, has a purplish color to it. And for each part, 4 characteristics are measured, and we're going to focus on the coating thickness. So what we're going to do is test to see if there might be differences in thickness among the 3 different color ratings. So I'm going to go to Analyze. Again, I'll go to Fit Y by X. I want to compare 2 columns, thickness and color rating. So X is color rating. It defines my 3 groups, and the measured response Y is thickness. So click OK, and we see our scatter plot. By the way, in the scatter plot, there is some evidence that the smutty black group may have a higher variance. We'll talk about that later on. And I'm going to click on the main report menu, and notice the second option is means ANOVA. The pooled t-test option is now gone because there are more than 2 groups to be compared. So I click ANOVA. You notice you're given the means diamonds. And by the way, again, the vertical tips are 95% confidence intervals for the true mean for each group. And notice there's no overlap whatsoever. This would indicate visually that all 3 groups may have significantly different theoretical mean values for thickness. Remember our ANOVA table, where the total variation measured by sum of squares, and it's not our goal to delve into all the arithmetic of the calculations, is divided up into 2 groups. Total sum of squares is the total measured variation among all 240 parts. We then divide it up into 2 groups. One part is the variation that occurs between the groups. That is there really a difference caused by the 3 different groupings? And then error, as R.A. Fisher, who invented the method, called it, or experimental error. This is the variation within the groups. Since all the measurements of the parts are within a group, there's no explanation for it, so Fisher just called it error. Today we might call it noise. So in essence, differences between the groups could be thought of as a signal that there may be differences between the group. The variation within the groups can be thought of as noise or simply error. And these sum of squares, these are totals. This is the total variation for each group. The degrees of freedom, if you see that column, tells us how many unique observations contributed to the estimate of the sums of squares. Since they're different, meaning each sum of squares is based on a different number of observations, we take averages. And R.A. Fisher referred to these as mean squares. These are variances. So we have the sample variance for color rating and the sample variance for error. The F ratio, or Fisher's ratio, it was named after him, is a signal to noise ratio. So 1 is sort of a baseline and would indicate there's no real effect, since the variation between groups is the same as the variation within groups. A high F ratio indicates that there is a significant difference among the groups, and again we rely upon a p-value to decide if the F ratio is large enough to be significant. So the F ratio is the analog of the T ratio or t-test. For two groups, the F ratio applies to more than two groups. Well, actually the F ratio is used for many things, but here it's a test for differences. Given the p-value is nearly 0, we say yes, the variation between the groups is significantly higher than the variation within the group. In other words, a high signal to noise ratio. So these mean differences we see between the groups are clearly much higher than the variation between groups. But there's an issue with the concept of ANOVA. It doesn't tell you which groups are different, it only tells you there are differences. And this was a problem Fisher recognized immediately around 1920, and it leads to what we call the multiple comparison group. That is, given the ANOVA has rejected and there appear to be differences, which groups are different. And this ends up being a problem because if you make a lot of comparisons between the groups, the more comparisons you make, the higher the chances you find false differences. In pharmaceuticals, this is sometimes referred to as the false discovery problem. Finding differences that are not real, and you can show in general the more comparisons you make, the chances of making false positives, finding differences that aren't there, go up very, very quickly. So over the years there have been many approaches to the multiple comparison method. There are hundreds of methods. We're going to focus on 4 of them, which is actually done in the JUMP software. And I'm just going to go ahead. I'm going to go through all of these with you and talk about them. And the methods we're going to talk about, Fisher originally proposed do all possible 2-sample t-tests between the groups. For a small number of groups this is fine, but when you start to have, say, 5 or more groups, the false discoveries go up very rapidly. There's something called Tookie Kramer, which is another approach to doing all the comparisons that are possible, but it does them in a manner that keeps the false discovery rate low. Unfortunately, it does this at the expense of finding real differences, and we say it's a low-power test. There's another method called Dunit. This is specialized. Dunit only makes sense if one group is a true control and you want to compare the other groups only back to the control. This was developed for the pharmaceutical industry to test for differences between a current batch and some master reference batch. So in Dunit's method, we don't make all possible comparisons, we only compare other groups back to the control. And then a method I particularly like is called shoes MCB, multiple comparison with best. This is a method that tries to find a treatment or a group that is in some ways best in terms of a largest or smallest response. So what I'm going to do is illustrate these methods using the anodized color data. So what I'm going to do is go up to the main report method menu to the left of one way and select compare means. First I'll do students T. Now notice these comparison circles. These are generated by JMP, and what they are, they're visual tests of significance. Okay, and the geometry of them is explained in JMP help. I will not get into the details of them, but if there is considerable overlap between any two circles, then they are not considered significantly different. So I'm going to click on the circle for purple black. Notice purple black is bold red. The other two groups are bold gray. What this tells you is purple black is significantly smaller than the other two groups. In fact, if I click on any group, the other two groups turn bold gray, indicating that all three of these groups are significantly different in the mean. And at the bottom of the report window, you get what is called a connecting letters report. This is an old method of reporting multiple comparisons, but it's very effective. So any group connected by the same letter is not considered different. So here all three groups have their own capital letter, therefore we conclude all three groups are different. So this is called compare each pair. Similarly, I'm going to select the option Tookie Kramer. By the way, HSD stands for honestly significant difference. If this method says the groups are different, they're very likely different, and it's not a false discovery. Okay. Once again, you get comparison circles, and if you click on one, it turns bold red, and if the others happen to turn bold gray, they're different. And once again, at the bottom, we get a connecting letters report. So here, the two approaches agree, but I'll show you in a moment this is not always the case. And next, I will do shoes comparison with better or best. So I'm going to select shoes method, and suppose a thicker coating is preferred. This is somewhat artificial. I click on it. So it says smutty black is significantly higher, or if I wanted a minimum, I could click on purple black, and what that indicates is that purple black is significantly thinner. And at the bottom of the report window, you're given, by the way, ignore this thing called LSD threshold matrix. It's really confusing. And simply take a look at the p-values where the groups are being compared, and what we see is smutty black is significantly higher, purple black is significantly thinner. Now, I don't have a control, so I'm not going to bother with Dunnett's test for this example. And I'm going to go back to my home window, and I'm going to take a look at the aluminum lithium data. Notice in the aluminum lithium data there are 8 batches, and I'm interested in testing for mean differences between the batches. So I'm going to go to Analyze, Fit Y by X. So batches X, KSI is the response. And I'm going to go to the report menu and select Anova. So notice this time We have a very low F ratio, it's only about 1.4, a large p-value indicating the variation between the batches really isn't much different than the variation within, and the variation within we consider noise. So at this point we cannot assume that there are differences between the groups, but for illustration I'm going to show you the compare means methods. First one, I'll click on the report menu and do compare each pair. So I'm going to click on H. Notice H turns bold red, C, D, and G turn red, so they're not seen as different, but A, B, and F turn black or bold gray, so we assume they are different. Okay. Remember, this method generates false discoveries, and with 8 groups, the probability is in the range of 0.75 that some of these differences could be false. And again, at the bottom, you get the connecting letters report. So notice from this report, I can say that H has its own letter and is different from B, F, and A. But notice there's considerable overlap. Okay, that's the student T approach. We did all possible 2-sample t-tests, and as you can see, there are a lot of them. As a matter of fact, there are 28 of them. High chance of false discoveries. So we might try the Tookie-Kramer approach. Notice for Tookie-Kramer, it finds no differences. As I said, Tookie-Kramer keeps the false discovery rate low, but unfortunately it does it at the expense of finding real differences. If you're looking for the ultimate solution to the false discovery problem and multiple comparisons, it does not exist. There are endless methods, and it's all up to the researchers to understand the methods and the relative risks of finding false differences versus finding true differences. And it's well beyond our scope to go into a deep discussion of multiple comparisons. People write textbooks just on that subject by itself. And then I'm going to go ahead and do Shu's method, and let's assume higher is preferred. So I'm going to click on B, which is the highest, and notice Shu's method says B is significantly higher than H, but it's not higher than the other groups. So maybe H stands out by itself as having less strength overall, but overall B and the rest of the groups except H are seen as potentially equal. And again, at the bottom you do get the connecting letter reports. Again, I don't have a control, but if let's just for assumption, let's assume H is a control. I'm going to click on H. So we're going to assume that was actually a control. Again, this is somewhat contrived, and we'll do Dunnett's. Okay. So I have to go down to scroll to the bottom to see Dunnett's. B is the control group. So it compares all other groups back to B. No other comparisons are done except those paired comparisons, and the only one close to being significantly different is H. So that concludes the discussion of ANOVA and multiple comparisons.